The F-14 is one of the few planes in history to ever feature a variable sweep wing, a mechanism that allows it to vary its wing angle from 20 degrees used during takeoffs and landings to a maximum of 68 degrees, which was reached at 0.9 Mach. There was even a special setting of 78 degrees, which overlapped the wings and allowed the F-14 to be stowed more compactly inside the aircraft carrier. This was a highly desirable ability because wing sweep is designed to manage how supersonic airflow interacts with the wing. This is how it works. Take a straight wing for a small Cessna. Airflow over a wing perpendicular to the free stream air has one component, the chordwise flow, which is air that flows over the chord of the aerofoil. The chord is the imaginary line running from the leading edge to the trailing edge of an aerofoil. Chordwise flow is how the wing generates lift, and it does this by accelerating the air traveling over the aerofoil. However, because the air accelerates, it can hit supersonic speeds before the plane does. Different wings can accelerate this flow at different rates. The speed at which the flow over the wing achieves supersonic speed is called the critical Mach number, and generally we want to make that number as high as possible to achieve a better lift-to-drag ratio. The variable sweep wing allows this. Let's look at the airflow components over the F-14's wing at its lowest sweep angle, 20 degrees. Here, we can separate the airflow into two components, the chordwise flow, which is now offset by a 20-degree angle relative to the free stream, and the second component, the spanwise flow, which flows along the length of the wing and does not accelerate, and thus does not lower the critical Mach number. At lower speeds, where supersonic airflow is not a worry, you want as much of that airflow to be chordwise. We need that lift. This is especially true for a plane like the F-14. It's heavy and needs to land on extremely short runways in the middle of the ocean. The slower it can fly on approach, the better. However, as the speed of the plane begins to climb, we are generating more than enough lift thanks to the increased airspeed, and thus can afford to convert some of that airflow into spanwise flow. We do this by increasing the sweep angle. Once at supersonic speed, the primary concern is no longer critical Mach number, but with preventing the supersonic cone emanating from the nose of the aircraft from intersecting with the wings and lowering the lift-to-drag ratio. So, in theory, adding a swing wing has a lot of benefits, but it is rarely implemented due to the complexity and weight of the systems needed to make it happen. And you can learn how the engineers of the F-14 overcame that challenge by watching the full-length Insane Engineering of the F-14 episode over on our YouTube channel, Real Engineering.